Let's talk a little bit about the Earth's magnetic field. In the study of astronomy, magnetic fields are a big deal, and they have a lot of places where they're very important around planets, around stars, and there are many, many phenomenon that we can only explain if we understand the concept of magnetic fields. Now, our Earth has a magnetic field around it that is very similar to the field that is around some sort of a bar magnet. Perhaps in your elementary school, junior high, high school, you may have played with bar magnets that have a north pole and a south pole. And a typical thing that we science instructors have you do is then cover this with another piece of paper and sprinkle some magnetic filings on top. When you sprinkle these magnetic filings on top, what happens is there is a pattern that emerges. And this pattern looks something like this, round circular swirls to the left and the right, and then lines going straight in at the top and the bottom. The interesting thing is, if you do this on a tabletop in a science lab, you get exactly the same magnetic field around the planet Earth. Now, the planet Earth does not have a bar magnet in the center. Its magnetic field is created in a slightly different way, but the field, the force field, is exactly the same shape. Now, we are seriously talking here about a force field, and a force field is some sort of a force that is emitted out into space. Magnetic fields are one type of force field, and another type that we have already talked about is the concept of gravity. Gravity is also a force field. So what actually causes the Earth's magnetic field? Remember we learned about the interior of the Earth by looking at seismic data, earthquake data. Well, we know that the center of the Earth itself is a solid ball, but around it is a large area that is actually liquid, and it is liquid iron and liquid nickel. Now, because of the fact that the Earth is spinning on its axis, our Earth is not stationary, it's actually spinning. What happens is inside of this liquid layer, there is motion. There is a large quantity of liquid metal that is actually rotating and spinning. Just the actual motion, the rotation of this metallic iron and nickel is what actually produces the magnetic field of the Earth. If you get any sort of metal that happens to be magnetic and you put it in motion, it will act just like a magnet. And depending upon the direction of motion, if it's all spinning in this direction, this is going to be the magnetic north pole, and this is going to be the magnetic south pole. Scientists have reproduced this situation in experiments on Earth, and that's how we can explain the Earth's magnetic field. Now, one of the other things that's really fascinating about the Earth's magnetic field is that it is not constant. The Earth's magnetic field changes. It changes its position, exactly where magnetic north is, and just to be wacky, it also periodically flips over. So let's talk about both of these. First off, the position change. This is a wonderful map, and it has some different dates on it, beginning back in the 1800s. And this shows where scientists in the last 200 years have actually mapped the position of magnetic north. In the 1800s, the magnetic north was many degrees of latitude lower than it is today. Over time, magnetic north has been marching closer and closer and closer to the geographic North Pole that you and I are familiar with as the top of the planet. Now, what's causing this change? Well, we think that this rotating fluid inside of the Earth's interior, the iron and nickel that's rotating in there, it does not rotate at exactly the same rate all the time. What makes this rotation rate change? Well, it has to do with the fact that our planet doesn't rotate solid. It does something which is called precess, and precess means that it is actually going to kind of wobble a little bit. Then the North Pole kind of shifts a little bit as it wobbles and as it rotates. That's going to have an effect on the interior of the magnetic field, magnetic liquid. The other thing is this fluid sometimes actually slows down and stops. This accounts for the fact that the magnetic field periodically flips over. About 50, 60 years ago, there was a research vessel that crossed North America, and they took, if this was North America here, and this was Europe here, what they did was they took core samples of the ocean floor, and they found along the mid-Atlantic ridge where magma was nice and fresh, coming right out of the interior of the Earth, all of the magnetic field lines pointed towards magnetic north. But if they went to the left or the right, they went away from that mid-Atlantic ridge, they found that earlier in time, the magnetic field was pointed the other direction, that north was the southern part of our planet. And if they went further out in time, rocks that were still older, the magnetic field pointed back north again. And then later, the magnetic field pointed back south again. So what that means is our magnetic field is not constant, and it does periodically flip. Now, the last flip was about 780,000 years ago. Some geologists think that we are due for another flip in about 10,000 years, probably not going to flip in your lifetime or my lifetime, but it is just a fascinating piece of information about our planet. Because of these shifts between where magnetic north is through time, magnetic north and true north are not at the same location on the planet. If you go traipsing around through the woods with a magnetic compass and you're trying to find your way back home, you and I who live in the Midwestern part of the United States are very, very fortunate, because the difference between where magnetic north and true north are is very, very small. That difference between the distance between true north and magnetic north is called magnetic declination. And again, that's a word you should know. This map here shows how much magnetic declination there is depending upon where you are in the United States. If you live in our part of the country, magnetic declination is 0, meaning true north and magnetic north are both aimed straight up towards the top of the ball. But if you happen to be in northern Maine, your compass will be as much as 20 degrees off. If you lived in northern Washington state, your compass will be as much as 18 degrees off. And this means that we are very fortunate in our navigating out in the woods with a compass. If you lived other parts of the country, the Northeast or the Northwest, you would definitely have to adjust for this magnetic declination when you go for a walk in the woods. Now, the Earth's magnetic field creates some fabulous and interesting events and phenomenon. And one of these is the auroras. So let's talk about, where do auroras come from? If you take the Earth's magnetic field lines and they extend not just around the planet, but way out into space, these are called the Van Allen belts. And there was an astronomer, his name was Van Allen, who actually first hypothesized the existence of this magnetic field out into space. These are the Van Allen belts. Now, we typically draw a magnetic field around a magnet looking like this because we draw it on a flat piece of paper. But the magnetic field around our planet is spherical. We are surrounded by it. It's sort of like we're in the center of a big beefy donut, and that big donut around us with not a lot of gap, that is the Van Allen belts. The Van Allen belts are just these areas of field lines going out into space. But the region of space where our magnetic field interacts with charged particles that are given off by other materials like the sun is called the magnetosphere. Magneto meaning magnetic, sphere meaning sphere of influence, area of influence. Now the magnetosphere is huge. It extends past the Earth millions of miles. This is an absolutely stunning picture. The sun constantly is throwing out charged particles. And when we say charged particles, we're talking about protons, neutrons, electrons, and other tiny little bits of ions and subatomic particles. These particles are aiming past our planet. Most of them are deflected around the planet by our magnetosphere, and that is a really, really good thing, because these things, this solar wind, can possibly cause a lot of mutations and a lot of cancers. Because we have a magnetic field on our planet, it's probably one of the primary reasons life evolved on planet Earth. Without that protective shield of the magnetic field, probably no life could have occurred. Now, this solar wind, as I mentioned, it is just very, very high energy particles that are thrown out by our star. As these particles shift past or fly past our planet, some of them do get caught, and they get caught in the Earth's magnetic field. When they do, when they actually get caught in the Earth's magnetic field, they follow the field lines, these force field lines. And the only place where these force field lines cut through the atmosphere is going to be at the north and the south magnetic pole. Now, without our magnetic field around us, we would not have an atmosphere. The sun solar wind would have blown away Earth's atmosphere long ago. And we start comparing to other planets, planets like Mars. Mars has a very weak magnetic field, and because it has such a weak magnetic field, it also has a very weak atmosphere. So there is a lot of pieces and parts that go into explaining the whole climate and weather of any sort of a planet. When you have this solar wind flying past the Earth and these particles, meaning electrons, protons, high energy particles, and they get trapped in one of these field lines, they enter the Earth's atmosphere at the north magnetic pole and the south magnetic pole. These particles kind of travel like superhighways on these magnetic field lines or Van Allen belts, and when they cross through into our atmosphere, they create high energy luminescence. They actually excite the molecules in the atmosphere, and that creates the auroras. The northern lights are aurora borealis, borealis meaning of the north, and the southern lights are aurora australis, just like Australia is in the south. These are the auroras down south where Australia is. There's a couple of videos of auroras I'd like to have you see. And when there is lots of solar wind activity, that's when you're going to have the maximum amount of auroras. So it's one of the many ways we get indications that the sun is spewing out lots and lots of interesting particles. All right, that will do for this one. See you later.